Imagine living in a world where your strongest sword could bend in battle, your sharpest knife dulled after a few cuts, and every civilization on Earth believed iron was the greatest metal humanity would ever possess. Then, somewhere in the smoke of an ancient furnace, someone accidentally created something far stronger. That single discovery would eventually reshape warfare, architecture, agriculture, and industry. Not because ancient people understood chemistry, but because they learned to master fire through thousands of years of trial and error. The invention of steel wasn't one breakthrough. It was one of the longest experiments in human history. Long before steel existed, humans had already fallen in love with metal. The earliest metals people worked were not hidden inside rocks. They fell from the sky. Thousands of years before anyone learned to smelt iron, rare meteorites occasionally crashed into Earth carrying metallic iron, mixed with unusually high amounts of nickel. Unlike ordinary iron ore, this metal did not require a furnace. It could be hammered directly into small tools, ornaments, or ceremonial objects. To ancient people, it must have seemed supernatural. A metal delivered from the heavens. Archaeologists have found meteoritic iron artifacts dating back more than 5,000 years. Some beads discovered in Egyptian burials were carefully shaped from meteorite fragments, while the famous dagger buried with Pharaoh Tutankhamun was forged from meteoritic iron whose chemical composition closely matches known meteorites. These objects were incredibly rare. Most people never even saw one. Iron from the sky was far too scarce to build civilizations. It became a symbol of prestige rather than a practical material. Meanwhile, ordinary life continued to depend on bronze. Bronze transformed the ancient world because it was harder than pure copper and easier to cast into useful shapes. Weapons became stronger. Axes stayed sharper. Farmers cleared forests more efficiently than ever before. Entire kingdoms rose during what historians now call the Bronze Age. For nearly 2,000 years, bronze appeared unbeatable. Yet beneath countless hills and mountains lay something far more abundant: iron ore. Humanity simply had no idea how to unlock it. Unlike copper, iron refuses to surrender easily. Iron ore is tightly bonded with oxygen, and separating the metal requires temperatures and chemical reactions far beyond those needed for earlier metals. Ancient people possessed the raw material. They lacked the technology, but as furnaces gradually became hotter through centuries of experimentation, one accidental discovery brought humanity closer to a new age: not steel, iron itself. Around the 2nd millennium BCE, scattered communities across parts of Anatolia, the Near East, and neighboring regions began achieving something that earlier generations could not. Their furnaces became hot enough to reduce iron ore into metallic iron, not molten iron, something stranger. Bloomery furnaces rarely reached the melting point of iron. Instead, they produced a glowing sponge-like mass known today as a bloom. Mixed with slag, ash, charcoal, and impurities, this lump looked nothing like the finished tools it would eventually become. The real work began after the furnace cooled. Blacksmiths repeatedly heated the bloom and hammered it with stone or metal hammers. Every strike squeezed out slag while compressing the iron into a denser, stronger material. Hours of labor produced only a modest amount of usable metal. It was exhausting, but it worked. Early wrought iron possessed important advantages over bronze. Although not necessarily harder, it was generally tougher and, most importantly, its raw material existed almost everywhere. Once communities mastered iron smelting, they no longer depended on scarce supplies of tin, one of bronze's essential ingredients. That changed history. Trade routes built around tin began losing their importance. Iron production spread steadily across Eurasia. Villages established small bloomeries near forests, where charcoal provided both fuel and the carbon needed during smelting. Mountains rich in ore became valuable resources, and skilled blacksmiths earned growing respect within their communities. Still, early iron had limitations. It bent, it dulled. Sometimes it cracked unexpectedly. Blacksmiths constantly searched for ways to improve it, even though they had no understanding of atoms, crystal structures, or carbon chemistry. They relied on observation, on experience, on countless failed attempts. And during one of those attempts, they noticed something extraordinary. An iron blade left in the fire a little longer sometimes emerged much harder than before. That tiny observation marked the first step toward one of humanity's greatest metallurgical discoveries. The blacksmith had no idea what carbon was, yet carbon was quietly changing everything. Every bloomery furnace burned enormous quantities of charcoal. As glowing iron remained surrounded by hot charcoal for long periods, tiny amounts of carbon slowly diffused into the metal's surface. The blacksmith could not see it happening, but the iron itself was being transformed. The result was remarkable. iron containing a carefully balanced amount of carbon became significantly harder than ordinary wrought iron while still remaining workable. Today, we call that material steel. No ancient craftsman invented it by understanding chemistry. They discovered it by paying attention. A blade, heated too briefly, remained soft. One overheated could become brittle. But somewhere between those extremes lay a sweet spot where the metal held a sharper edge and resisted wear far better than before. Finding that balance required extraordinary skill. Experienced smiths judged the fire by its color, listened to the sound of hammer blows, and watched how sparks flew from heated metal. These observations became their measuring instruments centuries before thermometers or laboratories existed. Knowledge spread through apprenticeship. A master rarely explained everything. An apprentice learned by watching thousands of repeated actions, copying every movement until instinct replaced uncertainty. Steel was becoming an art long before it became a science. Even so, producing consistent steel remained incredibly difficult. One successful blade could be followed by several disappointing ones because every furnace behaved slightly differently. That unpredictability pushed ancient metalworkers to keep experimenting. Some of the greatest breakthroughs were still ahead. One civilization became especially famous for taking steelmaking further than anyone else: ancient India. By at least the middle of the first millennium BCE, and possibly earlier in some regions, Indian metallurgists had developed a remarkable technique known today as crucible steel production. Instead of relying only on surface carburization, they sealed carefully selected iron together with carbon-rich materials inside small clay crucibles. The containers were placed into extremely hot furnaces. Inside those sealed vessels, something extraordinary happened. The iron absorbed carbon far more evenly than in ordinary bloomery methods. Under the right conditions, the metal partially melted, allowing impurities to separate while producing steel of exceptional quality. The finished ingots traveled astonishing distances. Merchants carried them westward through Persia and beyond, where skilled swordsmiths forged legendary blades renowned for their sharpness, toughness, and distinctive flowing surface patterns. Centuries later, many of these weapons became associated with the famous Damascus steel blades, admired throughout the medieval world. Modern research suggests that many of those celebrated swords were forged using imported crucible steel, produced in India, before being shaped by craftsmen elsewhere. Their reputation became legendary. Travelers described swords capable of keeping razor-sharp edges while remaining surprisingly resilient in combat. Although many later stories exaggerated their abilities, high-quality crucible steel genuinely represented one of the finest metallurgical achievements of the ancient world. Remarkably, the craftsmen who created it still lacked any understanding of atomic structures or modern metallurgy. What they possessed instead was something equally powerful: generations of observation, patient experimentation, and an ability to refine techniques through experience alone. The secret of better steel was no longer simply hotter fires. It was controlling what happened inside the metal itself, even if no one yet knew exactly why it worked. While Indian craftsmen perfected crucible steel, other civilizations discovered different ways to improve iron without using the same techniques. In ancient China, metalworkers followed a remarkably different path. By the late Zhou dynasty, and especially during the Han dynasty, Chinese furnaces reached temperatures high enough to produce molten cast iron. This was something bloomery furnaces in much of Europe and the Near East usually could not achieve. At first glance, that sounded like a breakthrough. It was, and it wasn't. Cast iron flowed easily into molds, making it ideal for producing farming tools, cooking vessels, and machine parts. But it contained too much carbon. That made it hard but also brittle. A cast iron sword could shatter under heavy impact. Chinese metallurgists refused to accept that limitation. Instead, they developed methods to reduce the carbon content of cast iron through repeated heating and exposure to air. This process gradually converted brittle cast iron into stronger, more workable steel or wrought iron. Without realizing it, they were controlling carbon in the opposite direction from many bloomery smiths. One process added carbon, the other removed it. Both pursued the same goal: better metal. Chinese engineers also built larger bellows powered by human labor and, in some regions, by flowing water. These innovations supplied furnaces with a stronger, more continuous blast of air, producing hotter fires and more consistent results. Technology was accelerating, not because someone understood chemistry, because generations of craftsmen kept solving practical problems one at a time. By the beginning of the Common Era, different parts of Eurasia had developed different metallurgical traditions, each remarkably sophisticated in its own way. The destination was similar: The roads were completely different. Steel did far more than improve weapons. It quietly transformed everyday life. A stronger plow could cut deeper into difficult soils, allowing farmers to cultivate land that earlier tools struggled to penetrate. Better axes made clearing forests faster. Durable chisels helped builders shape stone with greater precision. Reliable knives improved food preparation, leatherworking, and countless other crafts. Civilizations became more productive, not overnight, but generation by generation. A blacksmith was no longer simply a maker of swords. He became one of the most important specialists in the community. Kings valued skilled smiths. Armies depended on them. Farmers trusted them. Builders could not work without them. In many cultures, blacksmiths occupied a unique place between ordinary craftsmen and highly respected experts. Their workshops seemed mysterious. They transformed dull rocks into glowing metal, then hammered that metal into objects that appeared almost magical. To many ancient observers, it looked like alchemy. In reality, it was accumulated experience. Every successful tool represented hundreds of earlier failures. Every improved furnace embodied generations of experimentation. The invention of steel was never the achievement of a single genius. It was the combined work of thousands of unnamed craftsmen spread across centuries and continents. And despite everything they had accomplished, they were still only beginning to uncover what iron was truly capable of. The greatest revolution in steel would not come from discovering a new metal. It would come from learning to produce the same remarkable quality again and again with consistency, a challenge that would shape the future of civilization itself. One of the greatest obstacles facing every ancient steelmaker was inconsistency. A blacksmith could forge an outstanding sword one month and struggle to reproduce the same quality the next. The ore might come from a different hill. The charcoal could burn slightly hotter or cooler. The furnace walls might retain heat differently. Even the weather affected the process. Without precise instruments, every batch became a new experiment. Ancient craftsmen compensated with experience instead of mathematics. They judged furnace temperatures by the color of the glowing metal. Bright orange suggested one stage. Yellow-white hinted at another. The sound of the hammer revealed whether the metal was becoming too brittle or remaining too soft. Even the movement of sparks during forging offered valuable clues. Their senses became measuring devices. Generations of practice turned observation into extraordinary skill. Many workshops guarded these methods carefully. Families passed techniques from parent to child, while apprentices spent years performing simple tasks before being trusted with the furnace itself. Knowledge became a valuable possession, not written in books, stored in memory. That secrecy explains why certain regions became famous for exceptional steel. The advantage did not come from magic, it came from accumulated expertise that outsiders struggled to copy. Even when another blacksmith owned the same ore and charcoal, reproducing identical results without the same experience proved remarkably difficult. The real invention was not only the metal, it was the knowledge required to make it reliably. As steel improved, warfare inevitably changed alongside it. Early bronze weapons had already transformed ancient battlefields, but well-made steel introduced new possibilities. Steel swords could hold sharper edges for longer periods. Spears survived repeated impacts more effectively. Armor gradually became stronger while remaining practical enough to wear in combat. Yet steel alone never guaranteed victory. Training still mattered. Discipline mattered. Leadership mattered. A poorly trained soldier carrying an excellent blade remained vulnerable to an experienced opponent with an ordinary weapon. History repeatedly demonstrates this truth. Technology amplifies skill. It rarely replaces it. Outside the battlefield, steel continued influencing daily life in quieter, but equally important ways. Carpenters shaped stronger buildings. Stonemasons carved more accurately. Wheelwrights produced sturdier wagons. Farmers harvested larger fields. Every improvement in metal tools allowed people to accomplish difficult work with greater efficiency. Civilizations expanded because countless ordinary workers became slightly more productive than the generations before them. That gradual improvement is easy to overlook. But over centuries, those small gains reshaped economies, cities, and entire empires. Steel was not simply making better weapons, it was making almost every profession better. And perhaps the most astonishing part of the story is this. The people responsible for these achievements never knew they were manipulating carbon atoms inside iron. They solved one of history's greatest engineering challenges using observation, patience, and relentless experimentation alone. Sometimes the most important scientific discoveries begin long before anyone understands the science behind them. By the end of the ancient world, steel had become something far more valuable than a better metal. It had become a symbol of technological mastery. Different civilizations approached the challenge in different ways, yet they all pursued the same goal: producing stronger, more reliable tools from the materials nature provided. In the Middle East, skilled smiths refined carburization techniques over generations. In India, crucible steel reached an extraordinary level of quality that would influence sword-making far beyond its place of origin. In China, high-temperature furnaces and advanced casting methods created an entirely different path toward improved iron and steel. None of these civilizations copied a single master blueprint. Each solved the same engineering problem using local resources, local knowledge, and centuries of experimentation. That independent innovation is one of the most remarkable features of ancient metallurgy. It proves that human curiosity does not belong to one culture. It appears wherever people refuse to accept the limits of existing technology. Merchants carried steel across deserts and seas alongside silk, spices, glass, and precious stones. A fine steel blade could be worth an enormous amount because everyone understood what it represented. Not just a weapon. Thousands of successful decisions made inside a furnace. Every shipment spread ideas as well as materials. Blacksmiths observed foreign techniques, adapted them to local conditions, and slowly improved their own methods. Innovation traveled with trade. Today, producing steel seems almost ordinary. Modern factories create millions of tons every year using computers, chemical analysis, and precisely controlled furnaces. Yet the foundation of that industry was built by people who possessed none of those advantages. No thermometers, no microscopes, no knowledge of molecules or crystal structures, only experience, only observation, only persistence. When a modern metallurgist studies an ancient steel artifact, sophisticated instruments can identify carbon content, trace elements, and microscopic structures that explain why one blade performed better than another. Ancient blacksmiths had none of those tools. They reached many of the same conclusions through repeated trial and error. If a blade failed, they changed the process. If it succeeded, they repeated it. Generation after generation, those tiny improvements accumulated into techniques so effective that some continue to impress scientists today. This is why the invention of steel cannot be credited to one inventor or one civilization. It was a global achievement unfolding over thousands of years. Countless unnamed craftsmen contributed small discoveries. No single breakthrough transformed the world. Thousands of small breakthroughs did. That may be the greatest lesson hidden inside every ancient steel blade. Civilization is often built not by sudden miracles, but by ordinary people patiently improving yesterday's knowledge until it becomes something extraordinary. There is one final irony in the story of steel. The people who first created it never realized they had unlocked one of history's most important technologies. To them, the goal was simple: make a blade that stayed sharp longer, forge a plow that did not bend in rocky soil, create an axe that survived thousands of blows against hardwood. They were solving everyday problems. Yet those practical improvements slowly transformed entire civilizations. Better farming tools produced larger harvests. Larger harvests fed growing populations. Growing populations built larger cities. Those cities supported more craftsmen, engineers, merchants, and scholars. Steel became one of the invisible foundations beneath human progress. Long before railways, skyscrapers, or automobiles existed, ancient blacksmiths had already begun the chain of innovation that would eventually make all of them possible. Every generation inherited the knowledge of the previous one and added something new: a hotter furnace, a better hammer, cleaner ore, improved charcoal, a more effective forging technique. No single improvement looked revolutionary on its own. Together, they changed the world. The invention of steel reminds us that humanity's greatest discoveries rarely happen in a single moment. Fire was not mastered in one night. Agriculture was not invented in one season. Writing did not appear fully formed. Steel followed the same pattern. It emerged from thousands of years of observation, failure, adjustment, and persistence. From meteorites that inspired wonder, to bloomery furnaces producing spongy masses of iron, to blacksmiths unknowingly adding carbon, to Indian craftsmen creating remarkable crucible steel, to Chinese metallurgists developing entirely different methods. Each generation carried the story forward, not because they understood modern science, because they refused to stop experimenting. The next time you hold a kitchen knife, see a steel bridge stretching across a river, or watch a train rolling along metal tracks, remember that none of it began inside a modern factory. It began beside ancient furnaces filled with charcoal, where exhausted craftsmen watched glowing iron through clouds of smoke, trusted only their eyes, ears, and hands, and slowly uncovered one of nature's greatest secrets. They did not know about carbon atoms. They could not explain crystal structures. They had never heard the word metallurgy. But through patience, curiosity, and relentless experimentation, they created a material so important that no civilization has ever truly outgrown it. That is why the invention of steel was never just the discovery of a stronger metal. It was the moment humanity learned that with enough time, enough determination, and enough willingness to keep improving, even ordinary stone, fire, and iron ore could be transformed into something capable of shaping the future of the entire world.